Hello and welcome to CMG's webinar on mechanistic modeling of low salinity water flooding in clastics and carbonates. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Fraser Skoreko, Chief Reservoir Engineer at CMG, who will be presenting today's webinar. Fraser has over 35 years of industry experience and has been with CMG since 1993. He specializes in simulation of chemical, foam, in-situ combustion, and other advanced recovery processes. Fraser graduated with an engineering degree from the University of Calgary and started his career as an open-hole logging engineer at Schlumberger and Dresser Atlas back in 1978. He then moved on to work as a reservoir engineer at Gulf Canada in 1980, followed by working as a consultant in Tripoli, Libya from 1982 to 85. From 1985 to 1990, he worked as a staff reservoir engineer for Alberta Energy Company, currently in Canada in Calgary. Prior to joining CMG, Fraser also worked as a consultant in Mallorca, Spain on Libyan reservoirs for 3 years. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on the screen. We will post the recorded presentation on our website within 24 hours. You'll need to log on using the CMGL username and password to access the material. Fraser?
Thank you, Anjani. The outline of this webinar will be, first of all, introduction and concepts, then mechanistic modeling of low salinity water injection, or LSWI. Then midway through, we'll switch to some practical aspects. We'll look at the wizard that's in Builder for this process and go through a quick demo for carbonates with SO4. And we'll look at the same case with temperature effects and then conclusions. So first of all, the key variables affecting this process. The first one is reservoir lithology. For clastics, the presence of clay seems to be important. It's primarily kaolinite. And in the lab, there's no benefit observed in clastics in the absence of clays. Composition of crude oil seems to be important. The presence of polar compounds in the crude is necessary, and it's these polar compounds that give the rock the oil wettability. Again, in the lab, there's no benefit seen with synthetic depolarized oils. Presence of connate water seems to be important. There's no benefit seen with dry outcrop cores saturated with 100% oil. The divalent ion content, such as calcium, magnesium, in the water seems to be important. For clastics, it's SO4 that needs to be there. Or sorry, for carbonates, SO4 needs to be there. The mechanisms are, first of all, multi-ion exchange. For sandstones, it's concerned with cation exchange. For carbonates, it's anion exchange. Rock dissolution may be important. It's been shown in some SP papers that the transformation of chalk to other minerals, it was suggested as a mechanism for wettability alteration. Fines migration may be important. The release of these particles would improve the water wetness, and then the subsequent transportation of these particles would block some pore throats that may divert the fluid flow and increase the sweep efficiency, but it's also possible that the fines may cause plugging and be detrimental. Interfacial tension reduction effects may be important. There's a crucial salinity at which IFT between oil and water is minimum, but from the available literature to date, there's really no conclusions that can be drawn whether IFT is important or not for this process. Basic principles. First of all, the polar oil components are bound to the clay surface that makes the rock more oil wet. And this picture is showing how it may look on a molecular level. the oil being bound to the clay, and then there's these ion bridges in between the actual clay and the oil. The ion bridge composed of magnesium, calcium, sodium. Once the low salinity water is injected, it causes the ion exchange, the sodium exchanging with calcium, which would reduce this ion bridge and release some of these bound oil particles, which would result in a lower SORW and a shift to more water wet. There's also a pH increase by the chemical interaction between rock, the injected brine, and formation brine, and that may be caused by either cation exchange or carbonate mineral dissolution. Once the high pH occurs, it can react with the acid in the oil to give an in situ surfactant. If that occurs, then the surfactant will reduce the interfacial tension and change the wettability to more water wet. Then at the bottom of this slide, I just show the pH equations minus log of AH, and AH is the concentration of the H ion. Some examples of geochemistry. First of all, aqueous phase reactions. Some of the more common ones are the CO2 and the OH reaction. Then for carbonates, you have the NaSO4, MgSO4, CaSO4 reactions. For mineral reactions, some examples are the calcite-magnesite reactions. For carbonates, we have also dolomite and anhydrite reactions. For ion exchange reaction examples, we have sodium plus calcium, sodium plus magnesium, or sodium plus hydrogen. Or for carbonates, we have the SO4, the sulfate, with the carboxyl ion. Now the next three slides are designed to help understand the aqueous and mineral reactions in GEM. So first of all, the aqueous reactions are fast compared to mineral reactions, and for that reason the aqueous reactions are represented as chemical equilibrium reactions that occur instantaneously, whereas mineral reactions are represented as rate-dependent reactions. Now an example of an aqueous reaction is here, the CO2 plus water reaction giving H plus HCO3. Now in GEM, the keyword for defining the equilibrium constant is this log chem equil coefficients. You input 5 coefficients, and then with this equation here, you calculate the equilibrium constant. If for this case we substitute in 100 centigrade for temperature, we calculate our log KQ equals minus 6.43, and then K is 3.7 E minus 7, so quite a small number. Now the equations for the aqueous reactions are Q minus KQ equals 0. That's over all reactions. And then the Q is given by the product of AK to the power of VK. VK is just the stoichiometric coefficients, and then AK is given by this equation on the right here, which is gamma times M. The ideal case gamma is 1, so really it's just A as a function of M, which is molality or concentration. So essentially the KEQ, the equilibrium constant, gives the ratio of concentrations of products over reactants. And essentially KQ equals Q from this equation here. So if Q is less than KQ, then the equilibrium will favor the products. If Q is greater than KQ, then equilibrium favors the reactants. Now for this example, if you substitute in some numbers for the CO2 concentration of 0.1 molality, mole fractions of H and HCO3 are equal to a mole fraction of CO2, then Q is 1.9 E minus 5, which is greater than our KQ, so the reaction favors the reactant. So there's excess CO2 in the system, and a lot of it stays as CO2. However, if the CO2 concentration is now changed to be 0.01 molality, then the calculated Q is 1.9 E minus 7, which is now less than KQ, and now the reaction favors the products, and our H plus HCO3, our carbonic acid, is created. Now a mineral reaction example is given here, the calcite reaction. So again, we have our keyword giving us our 5 coefficients. We substitute in 100 again for temperature. We calculate KQ equals 4.81 for this case. Now the equations for the mineral reactions are a little different here. Here the reaction rate is given by our A sub beta, which is the reactive surface area, times K sub beta, which is the rate constant, given by this equation on the right, which is our normal Arrhenius equation, which has the activation energy, gas constant, and temperature. And then it's multiplied by this 1 minus Q over KQ. Now that ratio of Q over KQ, we call that the saturation index. So if that ratio is greater than 1, then dissolution occurs. If it's less than 1, then precipitation occurs. So for this case, if the molality of calcite is large compared to KQ, then mineral dissolution occurs, but it occurs at a rate governed by the rate constant and the reactive surface area. Now in GEM, we model the wettability alteration using relative permeability interpolation. The choices for the interpolant in the order of preferences are, first of all, the ion exchange, or the equivalent fraction on the rock surface of an ion undergoing cation exchange. Second choice would be the phase molality of any aqueous species, typically sodium, calcium, or sulfate. And then third choice is the porosity fraction change due to mineral deposition or dissolution. Now, GEM has been validated against a number of other geochemistry packages. It's been validated against FreeQC, Geochemist Workbench, and by Total using their internal software. This picture is showing a comparison against FreeQC. You can see that the two geochemistry simulators predict more or less the same results. Now, GEM has also been validated against laboratory data here. We see here in the picture is comparison against lab data. The lab data is the points, FreeQC is the dashed lines, and GEM is the solid lines. You can see that in this particular case, GEM gave a better match than FreeQC. Now, with both clastics and carbonates, CO2 seems to be a very important part of the whole process. And usually the oil will contain some small amount of CO2, maybe 1 mole percent or something like that. Then when you inject the low salinity water, what will happen is that the CO2 will partition more into the water. So you see down here at the bottom a plot of the CO2 solubility in water. You see at high salt concentrations, the CO2 solubility in water is fairly low. But as you get lower, like seawater here, or low salinity water somewhere here, the CO2 solubility in water becomes much greater. So that is why the water, or the CO2, will partition more into the water when the salinity is lower. So when that CO2 partitions into the water, then calcite will dissolve and provide a surplus of calcium that may or may not absorb. So in low salinity with CO2, the absorption of calcium will prevail in sandstone as opposed to calcium desorption. However, it's speculated that the change in wettability depends on the degree and amount of ion exchange, irrespective of whether calcium will absorb or desorb. So all of this together really means that the investigation of low salinity without the presence of minerals and CO2 could give erroneous results. Now in clastics, since ion exchange on the clay surface seems to be the driving mechanism, the modeling of the mineralogy and clay distribution is essential for getting good predictions of low salinity. And this table is just showing a typical water analysis from the North Sea sandstone reservoir showing the different ion contents. Now, there seems to be less understanding of low salinity effects in carbonates. There's quite a few difference of opinions as to the main mechanisms. So for that reason, I'll go through a short literature search here for carbonate. So the first paper here is by Hazim Al-Attar in the Buhasa field. It's showing that the increased calcium concentration of the injected brine resulted in decreased oil recoveries. So if you look at the plot on the left bottom here, other than the distilled water case, when the calcium concentration starts increasing, here the green curve is the lowest one, giving highest recovery. As it increases, your recovery starts decreasing. They also concluded that increasing the SO4 concentration in the brine changes the wettability to more intermediate levels and gave more oil recovery, but there also seems to be some optimum concentration. So if you look down here, the plot on the right, the distilled water case gives the minimum case, then a very small concentration of SO4, the green curves gives fairly high recovery. You increase it further, your recovery decreases. Then you get to this red curve, the 46.8, which goes up to the maximum, the optimum case. Then you increase the SO4 further, and your recovery now drops down to almost the distilled water case. Now this paper from the University of Denmark concluded that there is no effect observed on core floods at 25 degrees C, but at reservoir temperature 90 degrees C, they saw a substantial increase in oil recovery. They also saw that the formation of an emulsion phase was observed with an increase in the sulfate concentration at high temperature and pressure. So that emulsion phase is normally associated with surfactant and IFT effects. Now this paper from Abu Dhabi Petroleum Institute concluded that at 90 degrees C, the water wetness enhancement of carbonate rock is realized by reducing water salinity or increasing sulfate concentration, whereas the divalent cations had very little effect on wettability alteration. So their results indicated that the wettability alteration and fines migration may account for the favorable performance in carbonates. Now, this paper from the University of Texas, using flow simulation, not lab tests, showed that anhydrite dissolution contributes to wettability alteration, but it's not the main contributor. And the results of low salinity in carbonate rocks are best explained as wettability alteration due to the change in surface charge instead of anhydrite dissolution. Now this paper from Saudi Aramco concluded that the SO4 ions introduced alone are very actively absorbed onto the carbonate rock surface, increasing the surface charge. However, other water molecules cannot bind to the surface ion sites because they're already occupied by the SO4 ions. In another experiment they did, with all ions introduced together, they all interact with the carbonate rock surface, and the total surface charge change is based on the amount of ions introduced. Then Ousted concluded that with core flooding, the in situ generation of the sulfate ion created from the dissolution of anhydrite is the catalyst in the wettability alteration process. And dissolution of fines migration changes are due to the binding of the SO4 ions with the ions on the carbonate rock surface. Okay.
Before Fraser goes into the new builder wizard for modeling of low salinity water flood, I'd like to pose a question to our attendees today. And the question will show up on your screen. The question is, are you aware of the geochemistry capabilities available in GEM? And there are three options. You can respond by clicking on one of the three options. The options are, I have used geochemistry in projects before. The second option is yes, but have never used it. And the third one is no, I was not aware of it. The responses are coming back, and the system is analyzing those responses. Based on the responses here, it's 15% say I have used geochemistry in a project. Around 42% say yes, but have never used it, and 43% no, I was not aware of the geochemistry feature in GEM. So hopefully today's webinar will showcase some of the features and capabilities on geochemistry modeling that is available in CMG simulators, and hopefully you will get a chance to use them on your projects and evaluate geochemistry and low salinity water flooding as one of the potential recovery methods for your reservoir.
Okay, now I'll continue with some more practical aspects of modeling this process. So now I've switched to a live version of Builder, and I'll just show the process wizard. So I've got a typical GEM data set loaded. It does not have any aqueous reactions or components or anything. So I'll go to the Components menu and go to the Process wizard here, choose the option Low Salinity Water, click Next, and now we have the basic process wizard here. And the way it's designed to be used possibly multiple times. So right now what we see is the only thing that's really visible is our Rel-perm options. So if we already had an existing aqueous reaction structure, we could preserve that and then just change the Rel-perm options in case we wanted to do some history matching or something like that. Now in this case, we don't have anything. We can see here the number of aqueous components and mineral components are 0. So we need to create something. So we check this box here to change it. Now we see that we have some reactions available to be selected. Now we also have some defaults built in here. There are 5 defaults, 2 for clastics and 3 for carbonates. We're going to choose the SO4 option here for this demo. So I'll just go ahead and choose that. Now we see that the wizard has now given us some default reactions, aqueous reactions, some default mineral reactions. It's also populated some Rel-perm values, and it's allowed us to input some initial aqueous concentrations and mineral concentrations. Now, these are supplied by default. Now, if there's some reactions that you think you need to add, you can always add some more here by checking here. Now, you see here is a short list of the more common reactions for aqueous reactions, and here for the mineral reactions, a short list of the more common ones. Now, if you have some lab data or there's something you want to simulate that is not here, you can check this box here, and then it'll show all the reactions that are in the database. Now you can see the whole list of reactions, 500 some reactions here for aqueous, and for mineral reactions here, the whole list from the database again, many reactions which may or may not be relevant for your case. So now I'll switch back to the presentation.
At this time, I like to pose another question to the attendees, and the question is, Is low salinity water flood a potential EOR method candidate for your current or future projects? You can select it or respond by selecting yes or no on your screen. So it looks like responses are coming back in, and based on the responses received so far, which is 85% of the attendees have voted, 79% say yes, they have a potential candidate reservoir that is suitable for low salinity water flood modeling, and 21% say no. So in general, I think the methods described today will be really helpful on using this low salinity water flooding modeling capability on your current assets or even future projects.
Okay, I'll now continue with the looking at what the wizard has given us. So this slide is just showing how to load it in the wizard. Now, so this one is showing, describing a little bit more detail the results. So as I said before, we got some default reactions, aqueous and mineral reactions. It's also set some Rel-perm numbers and defaults for us. So it's set the SO4 ion to be the interpollant here, and it's also set the concentration to begin and end the interpolation and the number of Rel-perm sets. It's also set for us these SORW reduction numbers, and what those are is a ratio of the SORW from low salinity divided by the SORW from water injection for each Rel-perm set. Now, the reason a ratio is used so that multiple Rel-perm regions can be handled. You may have several or even hundreds of different Rel-perm sets, and each one may have a different SORW. So this is a method of reducing the SORW by the same factor in all those Rel-perm regions. And then the same thing is done for the KRW, again changing to be more water wet. We use a ratio of the KRW from low salinity divided by a ratio of the KRW from water injection for each Rel-perm set. There's also an option to change the curvature when the SORW is less than 0.1, in other words, when you have normalized Rel-perm curves. Now, with the Rel-perm curves, we can have two main different scenarios. So first of all, if your curves are normalized, in other words, if SWC is 0 and SORW is 0. Now that poses a bit of a problem because we're trying to shift the curves to be more water wet. And normally what we do is reduce the SORW. But if the SORW is already 0, we cannot reduce it further. So really the only way of shifting the curves to be more water wet is to change the curvature. So the top plot on the left is showing an example of a normalized curve. The blue curve is the water flood curve, and then the magenta curve is the low salinity curve, where we've changed the curvature to be more water wet. You can see the crossover points shifting to the right here. And here on the right is the same curves, except that's after block scaling, again showing our SORWs are the same because of our normalized curves. So the only way to shift it is to change the curvature. Now the second scenario is when we do not have normalized curves, and that's more or less the preferred method. You can still have block endpoint scaling, but non-normalized curves, in other words, SWC is greater than 0 and SORW is greater than 0. So this plot down here on the bottom right is showing how we just change, in this case, the SORW from 0.25 to 0.15. We don't have to change the curvature, and that's the preferred method. And the reason being is because many times our Rel-perm curves are from a history match. You don't really want to start messing around with the curvature because you may get unexpected results. So for that reason, it's not recommended to use normalized curves for this kind of simulation. Now I'll continue with this example with the SO4 interpolation. So I'm showing here the plot here is the same one from the literature search on carbonates of our SO4 concentration. If we take these values here and put them into a table, we can make a table here like this one on the right of our SO4 concentration, our recovery factors, and our SORWs from those recovery factors. And then now we can easily calculate our ratio of SORW. So in this case, our ratio of 0.482 is simply this number, 0.2152 divided by 0.4465. So these are the numbers we need to input to the wizard here. Also, what we need to input to the wizard is the pH of the formation water, in this case 5.22, and then the wizard will calculate the H ion for initialization. We also need to input mineral volume fractions. In this case, we input calcite and dolomite to be 0.5. Since it's a carbonate, we have high concentrations of both calcite and dolomite. We also need to input our initial formation water, concentrations of ions. We can click next in the wizard, select all the rock regions, next, enter our injected water composition, which is either seawater or low salinity water, and then click finish, and we'll be done in the wizard. I'm not going to show those steps here. So what we end up with here is what the wizard added. And as I mentioned, we got our aqueous reactions, our mineral reactions. It set our Rel-perm options here, plus our the numbers required of those Rel-perm options. It's also going to set our initial aqueous compositions and our initial mole fractions, or sorry, volume fractions of minerals, and our injected water composition. So now if we look at what the wizard gave us for Rel-perms, we can open the diagnostic plots in Builder and show the Rel-perm curves, and I've reproduced them here in this slide. The two pictures are the same Rel-perm curves. The one on the left is linear, one on the right is log. On the left plot, we can see the KRW change. It's using 3-point scaling, so our KRW at residual oil is changed. Our water flood curve is in red here. Our optimum case, our set number 2, is the green case here, giving us our lowest KRW. And then our slightly less than optimum case, the blue curve, is a slightly higher KRW. On the right here, the SORW, we can see the water flood case is 0.25. The optimum case, again set number 2, is here 0.25 times 0.482 or 0.12. And our slightly less than optimum case is the yellow curve. Now we look at the results. We can first of all compare the oil rate between the low salinity case and the seawater case. In this example, the injection begins 2015. And this example happens to have a oil production plateau that is imposed by the operator. So we don't see any low salinity effects until it falls off the plateau, and then we see some differences between the curves here. So in other reservoirs where you don't have this oil production plateau, you may see benefits from low salinity earlier, and that would of course depend on your withdrawal and injection rates. Now, if we look at oil recovery, the top plot here, we see that the low salinity case gives us about 9% incremental oil over the seawater case, which is substantial that's over 25 years. The bottom plot is our water cut. So with low salinity water, we have lower water cuts. Now, if we look at our ion concentrations, what we can do is do a property versus distance plot through the middle of our model, right through the injection well. So the very middle of this plot will be the injection well. So this is a vertical cross-section through it. So the top plot is calcium, middle one is magnesium, bottom one is sulfate. So we can see here the seawater case, the green curve, our calcium concentration decreases somewhat because with seawater the calcium is less than our formation water, and then of course low salinity water is even lower. With magnesium, we see again some drop in the magnesium content. For the seawater case, we do see a little bit of an increase in the middle here due to some reactions that are occurring. And then for the bottom plot, we see our most important parameter here for this case is our SO4 concentration. We see for seawater the SO4 actually increases. That's because the seawater actually has more SO4 than the initial formation water. And then the low salinity water is, of course, the lowest. Now, if we look at oil saturation and do cross-sections again, the same cross-section, we see the top plot is at 2018 after 3 years, and the bottom plot is after 25 years. So we see after 3 years that there's a significant oil saturation reduction, but it's fairly localized to the injection well after 3 years. But after 25 years, it's quite a large area where we see a good drop in the oil saturation. Now, if we look at the porosity changes due to minerals, we can again do a property versus distance plot through the middle. And what we see here is the seawater case in green is actually giving us a larger porosity change than the low salinity case. And we can also see that this is a negative change. So negative values mean precipitation. So with seawater, there's more precipitation occurring. Then the bottom plot here is the permeability reduction as a result of this porosity reduction. So we can see here that with seawater, there's a fairly significant permeability reduction of 0.8. Now, if we try to analyze that a bit in more detail, we look at the calcite reaction and our concentration. So our initial calcium concentration is 18,000 ppm. With seawater, it's much less. It's 511 ppm, and low salinity water is 26 ppm. So what happens is when the low salinity water is injected, and in this case either seawater or low salinity water, the CO2 will partition more from the oil into the water, as I explained previously, and then when that happens, then a CO2 reaction occurs in the aqueous phase that creates HCO3. Once that HCO3 is created, and when calcium is in surplus in the presence of that HCO3, it drives this equation to the left and causes precipitation. Now, if we analyze this further and we look at the calcite and dolomite behaviors, we see that they're opposite to each other. So the calcite is precipitating, the top plot here, negative values. Dolomite is dissolving, the bottom positive values here. And again, seawater is maximum. So again, if we try to analyze that in detail, we look at the two reactions of calcite and dolomite, we see that they're quite similar. The only difference being dolomite has the magnesium in there, but the main difference in this case is going to be the equilibrium constant. So for calcite, it's around 2. For dolomite, it's about 3.4. And because of that, the calcite reaction occurs at lower concentrations. So the surplus of HCO3 and Ca causes precipitation. And therefore, a deficiency of HCO3 and calcium ions are created and a surplus of H. This deficiency and surplus causes the dolomite reaction to go to the right and causes it to dissolve. Now, if we look at the pH changes with time, there's two movies here we can look at. The one on the left is seawater, one on the right is low salinity, so I'll just start the movies. So we can see that the seawater case, the pH is lower, so we have our higher pH with low salinity water. We can also see that the pH changes occur over a fairly large area. Now, if we do the same case and turn on the thermal option in GEM, we can now look at some temperature effects with this exact same case. So it's very easy to turn on the thermal option in GEM. We just need to supply a couple of thermal properties, the rock heat capacity and the rock thermal conductivity, put in a keyword thermal on, and then supply an injection temperature, and then run it again. Now, we can see here when we plot temperature that there's quite a large region of cooled down reservoir. So the actual region is quite large, showing that there could be quite a significant effect. Now we plot our oil recoveries, and what we see is that there's not really any change of the oil recovery. And that's because the oil recovery is really given by our Rel-perm interpolation, and we haven't really changed anything with Rel-perm interpolation. The SO4 concentration is still the same. So we don't see really anything different there, but we will see some differences in the SO and mineral behavior. So here we're looking at the SO. Top plot is after 3 years, bottom plot is after 25 years. The red curve is the thermal case, the blue one is the low salinity case. So there's not really much change after 3 years, but after 25 years we do see some changes of the oil saturation distribution. So there is some changes there with the thermal effects. But now when we look at the mineral reactions and the mineral precipitation, we see quite a large effect. And again, the red curve is the thermal option. The top plot is the delta porosity. Bottom one is the permeability reduction. We see that with the temperature effects included, there's really almost no delta porosity or no permeability reduction. And that's because at the very low temperatures, the injection temperatures of cold seawater, the mineral reaction rates are very slow. So I guess that's a fortunate thing. We don't see a lot of plugging. Now if we look at the pH between thermal and isothermal cases, the plot on the left is the low salinity case, one on the right is the isothermal. We see quite a large difference in the pH behavior. So in conclusion, we can conclude that GEM can model the low salinity water injection process for both clastics and carbonates using various mechanistic modeling methods to duplicate laboratory results using detailed geochemistry. And it's this mechanistic modeling that is essential to really duplicate things correctly. However, which method is selected is dependent on specific reservoir properties and on the laboratory results obtained, especially in carbonates. Temperature effects can be significant and should be included in the simulations.
Thank you, Fraser. We will now take up questions. If you have any questions and have not already submitted it, you can do so using the chat window on the right of your screen. Time permitting, we will try to answer as many questions as possible. However, if your question is not answered in this Q&A session, somebody from CMG will follow it with you individually within the next few days. I see there are several questions that are coming up on the screen here, and the first question is from George Dimitri, and he'll like to know is how much extra computing is required based on the number of reactions selected.
Okay, it's actually not the number of reactions selected, it's the number of components you use. So the time goes up pretty much linearly with the number of components. So it's usually, as you add one reaction, it's usually one more component. There may be some reactions where you add two more components, but what I would suggest is, for your particular process, just to begin with, use many reactions, all of them that you think may be applicable, and then run some sensitivities to see which reactions are really important or not. And then probably you can remove a number of the reactions, which will remove a number of your components to sort of optimize your runtime.
The next question is from Adidapo Ayolayo, and he'd like to know is there a possibility of including reactions that aren't in the database?
Yes, absolutely. The database is really just set up there for an easy method to include reactions. But if you have a reaction that is not in the database, you can very easily add it, but you would have to do that manually in a text editor in the GEM dataset.
The next question is from George again, and he'd like to know is, does the temperature option allow for over and under burden constant temperature effects?
That one I'm not sure of. It does in stars. I'm not sure GEM has that option yet. I could check on it and get back.
Okay. The next question is from Mehdi Banohar, and he'd like to know is, what are the screening criteria to decide which water flooding type we should select? Do we start with some lab experiment and then further optimize our process using the simulator?
You would really need to have lab tests. I mean, you can do some screening simulations and kind of guess as to what your parameters should be. I mean, there are quite a bit of literature values out there, some numbers that you can use from the literature, but of course your reservoir may be very different from what they used in the literature, so I'd recommend getting some lab tests.
The next question is from Rico Potivian, and he'd like to know is, does the mechanism take into account changes in capillary number, like that is the D-trap, along with the relative permeability shift?
For this process, you don't really need the capillary number interpolation. GEM does have that option, but we use that for different processes. For low salinity, you don't really need capillary number changes.
Okay. The next question is from Jeremy, and he'd like to know is, how do I get my geochemistry data in terms of reaction kinetics, and how do I validate that the geochemistry information that I've imported in my simulation model is correct?
Well, again, I would suggest if you don't really know what your geochemistry should be, I would suggest starting off with quite a few reactions. Maybe start with what the wizard gives you. You may want to add in a few more, and then you can run some sensitivities and try to eliminate some reactions and some components that are not really very necessary.
Okay. The next question is from Jose, and he'd like to know is, on which parameter is the KR interpolation based on in clastic reservoirs?
In clastic reservoirs, the interpolation should be normally based on calcium ion, the ion exchange for calcium. You can use ion exchange for sodium. You can also use the concentration, the molality of any aqueous component like calcium or sodium for the interpolation. But probably the recommended one for clastics is the ion exchange.
The next question is from Ibrahim, and he'd like to know is, does electrochemistry play a role in the low salinity water flood recoveries?
Well, yes, it does, and that's basically the cation exchange that we model.
Okay, the next question is again from Rico Potivian, and he'd like to know is, have you calibrated this mechanism to any field project for validation?
We have calibrated to lab tests. We have not yet internally calibrated it with field data, but some of our clients may have done that, but we might not be aware of that.
The next question is from Mehdi, and he'd like to know is, does asphaltene wax deposition in water injection projects happen? If yes, can we add these reactions phenomena to our deck files? In particular, there are some concerns when you have CO2 with the injected water.
Well, yes, there is asphaltene and wax deposition occurring in some reservoirs, especially with CO2. You will get asphaltene deposition, and GEM models that very well with the asphaltene option. That's something separate from the low salinity case that we're talking about today, but they can be used together. Like you can model both asphaltene deposition with the low salinity process.
The next question is from Arif, and he'd like to know is, how do you calculate the permeability reduction due to the porosity change?
Well, GEM has two different equations you can use for that, and you need to supply some parameters for those correlations. The default parameters in GEM are kind of average default numbers, so I mean that would be something you would have to calibrate using lab data, because your lab data may show some plugging that is either greater or less than what the GEM defaults are.
The following question is from Xianhui Kong, and he'd like to know is, what grid resolution is needed for accurate simulation of the reactions and the flowing process?
Well, for chemical floods, we normally recommend a maximum grid size of 10 by 10 meters. But now for low salinity, it's not quite so velocity dependent as chemical floods, so you could probably relax that somewhat. We don't have an exact number to use, but you could do some grid sensitivities to tell you what is the maximum grid size you can use.
Okay, thank you, Fraser. That's all the questions we had in today's session. We hope you have gained a better understanding of the mechanisms involved in the modeling of low salinity water flooding and the various features and capabilities available in CMG simulators. CMG does offer a multitude of training courses for all skill levels. For those of you who are interested in knowing more about low salinity water flooding, we do offer a one-day custom course on low salinity water flood modeling using GEM. We also offer company-specific customized courses on a variety of other subjects all around the world. For more information on our training courses, I invite you to visit our website at www.cmgl.ca. We will post today's recorded presentation to our website within the next 24 hours. Please log in using your CMGL username and a password to access the material. If you have any other questions related to the material presented today, or you'd like to know more about our other product offerings, please do not hesitate to contact us by email to sales@cmgl.ca. Again, thank you all for joining us for the webinar on mechanistic modeling of low salinity water flooding in clastics and carbonates. Thank you.